Time is tricky because, again, we have intuitive historical versions of what things mean, and then we have modern ultra precise definitions of these things. And so let's just start at the very beginning and clarify what each of these things are. To start with, we have to recognize that there's fundamentally two different ways of measuring time on the surface of the Earth. One of these is the conventional time that we use day to day. This is a version of time where 24 SI hours are exactly 86,400 SI seconds. And this is historically defined as the time that it takes for the sun to return to the same place in the sky. However, the Earth does not actually perform a full rotation about its axis in this period of time, because besides rotating about its axis, the Earth is also rotating around the sun. And so in the course of this 24 hours, the Earth has moved one full day's worth along its orbit. Since the Earth's year is around 365 days, that means that it has moved about a degree on its orbit. So if instead of tracking the time that it took for the sun to come back overhead, you consider the time that it took for a distant, quote unquote, fixed star to come back overhead, you would get a different result, and the result would differ by 1 degree, or 1/360th of the 24 hours, which works out to just about 4 minutes. And that measurement is known as sidereal time. And the mean sidereal day is just shy of 4 minutes less than 24 SI hours. And this is the time that it takes the Earth to actually rotate a full 360 degrees about its axis. And so we define our conventional solar, otherwise known as tropical year, as 365.24 and a bit days, and the sidereal year as just a bit longer than that. The previous discussion brought up this idea that time can be treated as an angle, and this happens a lot in astronomy. Observational astronomy is full of angle measurements as time, or time measurements as angle, because the Earth rotates, and it's very convenient sometimes to think about these things. And so we introduced this idea of hour angles. The hour angle is defined as the time from when an object was directly overhead. So a negative hour angle implies that an object is approaching. A positive hour angle implies that the object has passed you by. We have our mean equinox at the epoch, which is an inertially fixed direction, sometimes mapped to the vernal equinox direction or the modern definition of the vernal equinox direction. And from here, we can measure a lot of different angles. We can measure the azimuth angle of the sun. And if we are doing this measurement in an equatorial plane, this is the right ascension of the sun, as noted here. We can measure the angle to the Greenwich meridian, which is rotating with the Earth, and we call that the Greenwich mean sidereal time, or theta GMST. And then the difference between these two quantities would be the Greenwich hour angle of the sun, as denoted by this line. We can also measure the local sidereal time of our observer direction. And here I've just picked an observer at nighttime in Hawaii. And this is, again, just like the Greenwich meridian, of quantity that is rotating with the Earth. And this now is that theta LST value, the local mean sidereal time. And then there's the local hour angle of the sun, which is the sun's location with respect to your observer location. And the difference between the observer meridian and the prime meridian is given by the observer's east longitude by convention. This is all further complicated by the fact that there are two different suns at play here. And this is an important thing not to lose track of. So just to summarize what we've already established, the local hour angle is the Greenwich hour angle plus the observer's east longitude. The local solar time, which is defined implicitly by setting the local midnight at 0 hours, is the local hour angle of the sun plus 12 hours. This 12-hour offset is to make that 0 point in the middle of the night, which is most convenient for astronomers who tend to take measurements in the middle of the night. The Greenwich solar time is the prime meridian direction minus the right ascension of the sun plus that 12 hours. And as I said, there is an apparent sun where the sun actually is, and there is a fictitious mean sun. And that is a sun that has uniform motion along the celestial equator. That's just ticking along at the average rate of motion. And so we can define apparent and mean solar times. The mean solar time at Greenwich is traditionally defined as universal time. The motion of the Earth's pole, the fact that this is wobbling, is going to mess with this. And if you correct for that motion, you get a small deviation from UT naught, that mean solar time, and this is called UT1. And typically the difference, the absolute difference between UT1 and UT naught is on the order of 30 milliseconds. Historically, there have been additional corrections applied and there has been a UT2 definition, but in modern usage that has been dropped. And if you need more precision, there's different systems that you switch to. So in terms of universal time, there's just UT naught, which is uncorrected, and UT1, which is correcting only for the Earth's pole motion in the International Celestial Reference Frame. So now finally, we can get to a definition of the theta LST, the local sidereal time value. And typically we calculate it by using a lookup table of reference values at some epoch, T naught, and then we add the rotation of the Earth, that definitional omega E from WGS 84, times the time since epoch, and then we add our observer east longitude. You can get tabulated values from the astronomical almanacs, which are joint publications of the US Navy and the British Royal Navy. There's multiple other reference sources online and various civilian sources. So this information is widely available and also coded into a bunch of existing software packages. There's also long-term average fits to these values. So you could calculate theta G naught using equations such as this one, which are functions of the number of Julian centuries as measured from the year 2000. So now we have to define what a Julian century is. The Julian century is a measurement of the Julian date, which has nothing to do with the Julian calendar or Julius Caesar. It actually, Julius was the name of the father of the person who invented the system. And this is a very complicated system that is essentially measuring the number of solar days since January 1st, 4713 BC. That choice of 0 point is the result of a combination of many different naturally occurring cycles, including a 28-year solar cycle, a 19-year metonic cycle, the Roman indication, which is an ancient calendar system, was a 15-year cycle. These all have a common point in 4713 BC, and so this was set as a 0 point and then allowed to march on. A Julian year is 365.25 days exactly, the first two decimal points of our tropical year. A Julian century is exactly 100 Julian years. And so this equation here gives us a way of evaluating the Julian date as a function of the current calendar date. And because these give very, very large values, we also sometimes define a modified Julian date, which is just knocking off 2.4 million, 0.5 Julian days off of the Julian date. And so there you will find a lot of equations in the astronomical and astronomic literature that are fits to Julian days or Julian centuries. On top of all this, there's a few more important time systems to keep track of. There's coordinated universal time, or UTC, which is the time that your computer or phone tells you. UTC is an approximation of UT1 based on atomic time, where atomic time is just a weighted average of over 400 atomic clocks spread all over the world. And so it is a consensus definition of the steady tick of time as experienced on the Earth. UTC is adjusted periodically with the addition of leap seconds so that it tracks UT1 to within 1 second. The latest leap second was added to UTC all the way back in 2016, which means that TAI is currently 37 seconds ahead of UTC. Leap seconds, by international agreement, are only added at the very end of the year or very infrequently at the middle of the year. Most typically, leap seconds are added at the very, very last second of every calendar year. GPS time is the time that the GPS constellation uses, and it is fixed as the UTC time in 1980. At that point, UTC was off from TAI by 19 seconds, so GPS will be off from TAI by 19 seconds for all time, but will drift further away from UTC as more leap seconds are added to UTC.